Hello everybody, my name is Artemiy Margaritov, and today I'm going to tell you about inefficiencies of the virtual memory subsystem in public clouds, and present our technique PTEMagnet that mitigates them. This work was done at the University of Edinburgh, and it is supported by the Google Faculty Research Award. Let me start with a small introduction and tell you what environment frequently occurs in a public cloud, for example, Google Cloud, AWS, or Microsoft Azure. So firstly, public clouds run workloads with large datasets, such as databases, key value stores, and analytic frameworks. Large datasets lead to frequent TLB misses that are resolved by page walks. As a result, public cloud workloads often experience a lot of page walks. Secondly, to provide security and simplify resource management, cloud providers rely on virtualization and run applications inside virtual machines. And lastly, applications are often collocated in the same virtual machine. Application collocation is used to increase utilization of virtual machines with many virtual CPUs or vCPUs. Virtual instances with many vCPUs usually offered with a fixed RAM to vCPU ratio. For example, Amazon Elastic Cloud offers virtual instances that can be scaled to 64 vCPUs and have 4 GB of RAM per vCPU. Thus, a virtual machine with 64 vCPUs has 256 GB of RAM. It is difficult to utilize both compute resources and RAM resources at the same time with just one application. And application collocation solves this problem and increases utilization of virtual machines. We studied the environment that has all three of these features, and we found that on a Linux-based operating system, in such an environment, there is a performance bottleneck in the virtual memory subsystem. The performance bottleneck is created by combined use of virtualization and application collocation. Namely, such a combination makes page walks longer. To understand what are the sources of the performance bottleneck, let's review the virtual memory basics. So, mappings of virtual to physical addresses are stored in a page table. Under virtualization, both guest and host page tables are implemented as radix trees whose leaf nodes are called page table entries or PTEs. Each PTE is 8 bytes. As a result, 8 PTEs can fit into one 64-byte cache line. Moreover, a cache line contains PTEs for nearby virtual pages. On a TLB miss, the page table is sequentially traversed, and this procedure is called a page walk. On x86 and ARM architectures, under virtualization, page walk can take up to 24 serialized memory accesses. Alright, let's now see why under virtualization, page walks become longer in application collocation compared to standalone execution. To understand why page walks become longer, firstly, we studied from where in the memory hierarchy page table nodes are served during a page walk. We compared two configurations, execution in collocation with a memory-intensive corunner and standalone execution. It's important to note that in collocation, we pinned threads of a target application and a corunner to cores of different processors. As a result, the target application and the corunner don't share LSC capacity, and there is no cache contention. However, despite the fact that there is no cache contention, we found that in collocation there are more cache misses during accesses to host PTEs than in standalone execution. So the question is, why in collocation there are more misses to host PTEs? And the answer to the question is that an increased number of cache misses during accesses to host PTEs occurs due to the lower locality of host PTEs in collocation. Namely, in collocation, host PTEs of nearby pages are not located in the same cache line, but are scattered among multiple cache lines. As a result, the host PTE footprint is larger in collocation than during standalone execution. During standalone execution, page walks, translating addresses of nearby virtual pages, read PTEs from just one cache line. In contrast, in collocation, page walks, translating addresses of nearby virtual pages, fetch multiple different cache lines and don't benefit from locality. So now the question, why collocation scatters PTEs among multiple cache lines? We found that the poor cache locality of host PTEs stems from fragmentation in the guest physical address space. The fragmentation is created by the Linux memory allocator in the guest operating system. Let's now talk about how the Linux memory allocator affects cache locality of host PTEs. To understand the relationship between fragmentation in the guest physical address space and locality of host PTEs in collocation, let's first talk about standalone execution. During standalone execution, for subsequent page faults, the Linux memory allocator in the guest operating system is likely to assign physical pages from a contiguous region. Thus, pages that are contiguous in the guest virtual address space, which is in an application's perspective, are contiguous in the guest physical address space. Meanwhile, the host virtual address space features the same contiguity as the guest physical address space. As a result, contiguity is propagated from the guest virtual address space to the host virtual address space, meaning that whatever is contiguous in the perspective of application is contiguous in the host virtual address space. Now, let's consider execution and collocation. In collocation, the Linux memory allocator assigns physical pages to applications using first-come, first-served policy. As a result, if page faults of different applications interleave with each other, the Linux memory allocator breaks contiguity in the guest physical address space. Consequently, the lack of contiguity in the guest physical address space leads to the lack of contiguity in the host virtual address space. As a result, contiguity is not propagated from the guest virtual address space to the host virtual address space. To sum up, in collocation, the Linux memory allocator scatters pages all over the guest physical memory, making pages that are nearby from a perspective of an application distant from each other in the host virtual address space. Okay, how is that related to the footprint of host PTEs? Well, recall that a cache line stores 8 PTEs for pages that are nearby in a virtual address space. But in collocation, pages that are nearby from a perspective of application, the guest virtual address space, are scattered in the host virtual address space. That is why host PTEs are scattered among different cache lines in collocation. To put everything together, during standalone execution, there is no fragmentation in guest physical memory, and contiguity in guest virtual memory is propagated to host virtual memory. Host PTEs corresponding to nearby applications pages are packed into one cache line, and page walks can reuse this cache line. In contrast, in collocation, fragmentation in physical memory of the guest operating system leads to fragmentation in host virtual memory. This results in fragmentation in host page table and destroys cache locality of host PTEs. As a result, page walks become longer. Alright, we understand what the root cause of the problem is. Let's fix the problem and restore page walks performance in collocation. The root cause is fragmentation in the guest physical memory. We can prevent it by enhancing contiguity in the guest physical address space. But how much contiguity do we need? Recall that There are only up to 8 PTEs in one cache line. If we create contiguity among 8 pages, we will achieve the maximum possible locality of host PTEs. As a result, enhancing contiguity in just 32 kilobyte region is enough. So here's an idea. Let's use a reservation-based allocation policy to guarantee that all physical pages from a 32 kilobyte region are always allocated to the same application. This brings me to our proposal, PTEMagnet, that is a reservation-based physical memory allocator enhancing contiguity among 8 physical pages in the guest operating system. PTEMagnet is designed for accelerating page walks in collocation. Let's talk about PTEMagnet in more detail. As I said earlier, PTEMagnet is a custom physical memory allocator for the guest operating system. PTEMagnet can be implemented as a patch for the Linux kernel of the guest operating system. So how does PTEMagnet work? On a page fault, PTEMagnet firstly, in virtual address space, finds a 32 kilobyte region to which a faulting virtual address belongs to. Then PTEMagnet checks if a region of physical memory has been allocated for this region of virtual memory. Further, PTEMagnet makes one of the following two actions. If no region in physical memory has been allocated yet, PTEMagnet reserves a new 32 kilobyte region in physical memory and returns a 4 kilobyte page from the reserved region to the application. In contrast, if a region has been allocated previously, PTEMagnet returns a 4 kilobyte page from that region. Let's now discuss PTEMagnet's overhead. PTEMagnet has negligible overhead as it is invoked only when physical memory is allocated or deallocated. When invoked, PTEMagnet performs just very quick check if region has a reservation or not. PTEMagnet is a software-only technique, and our implementation takes just about 500 lines of Linux kernel code. PTEMagnet requires a modification of the guest operating system that is allowed by many cloud providers, for example AWS or Google Cloud. As a result, PTEMagnet can be enabled just by cloud users without involvement of cloud providers. And the last but not least, PTEMagnet never slows down applications. We prototype PTEMagnet in the Linux kernel and compared it with the default Linux memory allocator. As a metric of performance, we measured execution time on a dual Intel Xeon-based server running Ubuntu 18. We used QEMU to run a virtual machine. We evaluated multiple applications, such as graph analytics applications, and selected spec benchmarks, including compilation and data compression benchmarks. As co-runners, we used various representative cloud applications that are listed in the paper. Moreover, we found that just one benchmark, MLPerf inference for object detection, can cause high fragmentation in the guest physical memory and slow down page walks a lot. The chart on the slide shows performance improvement delivered by PTEMagnet in collocation with MLPerf inference object detection benchmark. We can see that PTEMagnet boosts performance by 4% on average and by 9% in the best case. Before I finish, let me just briefly summarize the key findings. We found that in presence of virtualization and application collocation, page walks become longer. It happens because the Linux memory allocator in the guest operating system fragments host virtual address space. Consequently, host page table entries of nearby pages are getting scattered among multiple cache lines. As a result, there are more cache misses during page walks, and page walks become longer. In response to these observations, we propose PTEMagnet, a reservation-based physical memory allocator for the guest operating system. PTEMagnet restores performance of page walks in collocation. PTEMagnet is completely software solution, it takes just about 500 lines of code and can be enabled by cloud customers without involvement of cloud providers. Our evaluation shows that PTEMagnet delivers up to 9% performance improvement and never slows down the system. This brings me to the end of my presentation. Thank you for your attention.